Oh, hi everyone. Thank you for showing up for your learning. Today I am pleased to take you through some trigonometric topics. Not this, although I'll assure you trigonometry is very much alive and well in this weird lava lamp graph. But here, let's take a look at angles in standard position. Some of you have been saying trigonometry is the study of triangles, and some other mathematicians would say that trigonometry is one of the most misnamed subjects in math. It's more properly the study of circles. And today we're going to liberate trigonometry from triangles and get it more into a circular type of bent here. Okay, so we're going to see angles that don't occur in triangles, angles such as like bigger than 180 or negative angles. We're going to see those today. So now we're going to move our angles in our trigonometry to the coordinate plane. Notice that the coordinate plane is labeled with this as the positive x-axis. This is the negative x-axis. This is the negative y-axis. And this is the positive y-axis. And then we label the four different regions of the plane this way, where this is the first quadrant, second quadrant, third quadrant, and fourth quadrant. All right, well, let's keep going. First quadrant, x and y are both positive. Second quadrant, x is negative, y is positive. Third quadrant, both are negative. And in fourth quadrant, x is positive, y is negative. Let's keep going. So here's some vocabulary for you. An angle in standard position, it's going to have to do with where the initial arm and terminal arm are. So we need to understand what the terminal arm and the initial arm are. So I'll talk to you about those. We're going to see that we're going to have angles that are like angles away from the positive x-axis. And then we're going to have the angle there. This here is called the terminal arm of the angle. It's like where the angle rotates to and finishes. This is the angle that we're interested in, is that angle we're opening up. And the initial arm is where the angle started. And the initial arm is always the positive x-axis. The positive x-axis. It's one of those things that we want to see some examples and use this vocabulary over and over again so we can figure it out and start remembering it. Let's take a look at some standard position angles with the terminal arm and initial arm. Oh, yeah? Okay, sure. I'll hold on here for a second. I'll talk through some other examples. Someone give me an angle between 0 and 360. 180. So here is an angle of 180 degrees. It would be like that. Its initial arm is here at the positive x-axis, and its terminal arm is over there, actually the negative x-axis. So that would be a 180-degree angle. Someone give me another one. 359. All right. Okay, so 359 would look like this. It would be, I go all the way around and stop just before the x-axis. So the terminal arm would still be there at 0, 0, and it would come out there. And that would be 359 degrees. The terminal arm would be that line just below. Well, it's just like it's on an angle just below the positive x-axis. It's negative 1 degree below the x-axis, or it's positive 359 degrees around. And we'll find that negative 1 degree and positive 359 degrees are different ways of saying the same thing. Okay. Give me another one. While people write down the definitions, these good students, not just taking a picture. You're not going to give me a number, eh? Just like no. 1. Give me one that has a better diagram. Something that's not near one of the axes. 5. 95. Good. Okay, great choice. So 95 degrees. Here is 90. And then a little bit more is 5. Here is the terminal arm. And this is the initial arm. Notice the initial arm in all of these is always the same. The terminal arm is over here, just wherever that arm ends up. And that's the angle that opens up. This is 95 degrees. This angle, 95 degrees. This would be 5 degrees from 90, 5 degrees. This would be 85 degrees. going that way. Okay, let's keep going. 275. 275. 275. 270 would be the negative y-axis. Okay, so we're only going to, and I'm never going to try and trick you about this, except maybe I would, but I don't think I ever have. We're only going to be looking at standard position angles, okay? You got to remember that you got to set your rotating point at 0, 0. And the terminal arm is always this thing that opens up away from the initial arm, which is here. Okay, these are non-standard angles. We could put them into standard position, but right now they're not. This one, it's not rotating around 0, 0. This one didn't rotate from the x-axis. It rotated from somewhere else. So they different. This is what we're talking about. Standard position angles. Let's go. So let's figure out which quadrant each one of these angles belongs in. Okay, a 60-degree angle, which quadrant will that be in the end of the day? 1, good. We open up a 60-degree angle here. It's going to look something like that. Something like this, 60 degrees. There, that's 60 degrees. Good. The next one is 300 degrees. Where's that going to end up in? Avery. That's going to be in the fourth quadrant, 300 degrees. How did you know, Avery, that it's going to be in the fourth quadrant? Oh, yeah, well, 270. Let's count here. I'm going to count by 90s. Counting by 90s is something that I'm pretty good at doing because it's not hard. And here I count 90, 180, 270, and then 270, I want to go another 30. So that's about there. That's about what a 300-degree angle would look like. All right, 150 degrees. In quadrant 2. How do you know, Caden?
Like if you add
yeah.
Between 180 and 90.
Yeah, it's between 180 and 90. So I go over here. There's 90, and I need to go another 60. So it's something like that. And then there, that would be my 150-degree angle. 150 or so. Good. So that's in quadrant 2. This one was quadrant 4. This one was quadrant 1. And we have 1 in each one, right? So this one, by process of elimination, is in 3. Why is 210 in 3? Yeah, it's before 270, and it's after 180. So it goes all the way around here, it goes to 180, and then adds another 30 degrees, so it's there. That's 210. Cool. Cool. Now, for these different angles, we might want to know what's the value of sine 210, or what's the value of cosine of 210. And it would be useful to be able to guess, will the sign be positive or negative? By the sign, I don't mean the S-I-N-X. I mean, will it be a plus or be it a minus after when we evaluate it? All of these trigonometric ratios can be either positive or negative. Connor, that video is going to be there after I'm done talking, so save it. So we want to know these things. And the CAST rule is one memory trick that you can use to memorize this thing. The way you use it is you remember CAST is spelled C-A-S-T, and for some reason we go this way from the fourth quadrant all the way to the third quadrant there to spell CAST. And then what that tells you is up here, sine, cosine, and tangent are all positive. Over here, only sine is positive. Over here, only tangent is positive. And over here, only cosine is positive. Each one of the trigonometric ratios has the chance to be positive in 2 quadrants. So you use the CAST rule to know cosine is positive down here. All of them are positive up here. Sine is positive over here. And tangent is positive over there. It's a quick memory trick. You'll figure out why, or I'll try and show you why, by the end of this lesson. He says, looking at the clock. Okay? All right? Let's keep going? Yeah. Okay. So let's figure out the sine of these angles. And by sine, we now have a math pun, a homonym there. So I want to be clear. Is it positive or negative? Sine 45, is that going to be positive or negative? How do you know that's positive? Because you've done sine 45 on your calculator before and it gives you a positive number, 0.707-ish. Yeah, that's a good way of thinking about it. But also, we know that sine 45 is in this quadrant, and according to CAST, you very quickly put one of these diagrams down on your test or on your cheat sheet or something, and you notice, okay, I opened 45 degrees, I'm still in the first quadrant, and all of them are positive. So sine is positive, and so would tangent and cosine for 45 degrees. All right, cosine 223, is that positive or negative?
Negative.
It's negative.
How do you know it's negative? Because the cast rule, bro. Yeah, okay, so carry on. Explain it to us.
The cash rule determines, it says that in quadrant 3, everything will be negative. And as we know, since it's how long is it? 223, that's cost 180 and not 270, so it's in between there.
Yeah, so this one, 223, is in here somewhere. And yeah, that's going to be negative because only tangent is positive down there. Oh, and sorry for calling you bro. I just tend to get a little triggy with it when the math gets this fun. Okay, so let's keep going. Don't let me distract you. This one's negative.
Are we supposed to be drawing them?
Yes.
I know I messed with the tables, but
I would definitely visualize all of these angles on my mental whiteboard. Tangent 157. See it. 157 weighs not quite 180. It's definitely between 180 and 90. It's pretty close to 180. So I'm seeing boop that. And then it goes up there. And then I see, oh, it's in the second quadrant. Wait, now I want the tangent. Is that going to be positive or negative? Why? It's in the second quadrant. Yeah, tan 157 is in the second quadrant. And only sine is positive in the second quadrant, so it's negative. Sine 145. Yeah. And that was on your table, was it? I don't know. You had a table of trigonometric values memorized.
I didn't draw a 10.
Up to 90. Okay. Well, what if I told you that with this information, you could expand your table that's already exists in your mind up to 90, up to 360 and beyond. Yeah, it's pretty good, right? And it can all this can be yours for 3 easy payments. Yeah. All right. So this one's positive because sine is positive in the second quadrant, and that angle 145 is somewhere over here.
Isn't tan 157 incorrect? Tan 157 should be in the second quadrant, not the third.
Yeah, it is. Tan 157 is in the second quadrant. And sine is positive there. Cosine and tangent are both negative.
Wait a second. Tan 157. You're still starting in the first quadrant, right?
Right.
So you go 1, so 90 degrees, and then 180 degrees, but it's 157.
157, yeah, somewhere over there.
Right. Oh, you just did draw on your diagram.
Yeah, somewhere like that. That's tan 157. I drew it on this diagram, Ben.
The last one's positive, right?
Sorry?
The last one's positive.
Yes.
So
And Camden, tell us why cosine 315 is positive.
Well, I mean, it's in the fourth one, and it's a cosine positive.
There you go. Yeah. So now we know how to use the cast rule. You figure out which quadrant the angle's in, and then use cast to say, is that trigonometric ratio going to be positive or negative? Cool. I think it's cool. Now, let's take a look at this idea of related acute angles. And this is going to be key for you to expand that knowledge that you have between 0 and 90 degrees to other quadrants. Okay? All of these different angles have what are called related acute angles. And we're going to find relationships between their trigonometric ratios and the trigonometric ratios of their related acute angles. They're also called reference angles, and I usually call them reference angles. So that's why I put in this note, they're also known as reference angles. So I think of them more, we refer to these angles to figure out stuff about these bigger angles. Okay? If we're in the first quadrant, okay, in all of these cases, the beta angle is the reference angle. And the theta angle is the angle of interest. So if I'm interested in a theta that happens to lie in the first quadrant, the reference angle is equal to theta. It's very simple. It is its own related acute angle. That should not be surprising. Every angle between 0 and 90 degrees is acute. And then if we're in the second quadrant, well, now we have to do a little bit of math to figure out the related acute angle. Let's say theta is some angle that would fall in the second quadrant. We'll call it 110. What would the related acute angle be in this case?
110. No. It's 80.
How do you know it's 70?
90,
Yeah.
Sorry, 70.
So we use a little formula here. 180 degrees minus your angle of interest will give you the related acute angle if you're in the second quadrant. I don't recommend memorizing these little formulas. We're going to have 4 such formulas for the different quadrants. I recommend using visualization to understand them. So, but you can also just copy them all down onto your cheat sheet. That would be fine. But here, I noticed that if I went 180 degrees and then went back some number of degrees to 110, I must be going back 70 degrees. And so then I can kind of figure out, well, whatever angle that is in there, I take 180, subtract that angle, and that gives me my reference acute angle. If I'm way over here, let's say that this is 235. 235 degrees, what would my beta be?
235, so 90, 235, 270 minus 235.
Sorry? No. Happens to be one of my favorite numbers. Showed up in the explode it problem.
It's not 35?
Wouldn't it be B subtract 180? Or sorry, B subtract.
So it's wait. So it's 270 for the
Well, let's take a look at it. If I want to know how much I have to go back here to get to the beta there, I would take theta and subtract 180. Okay? I take the theta, but then I subtract this part of it,
Oh.
and it leaves me that part.
But couldn't you also do the B plus 180? Yeah, but if
Beta plus 180 equals theta. Yeah. Beta plus 180 equals theta. That's just the same equation rearranged. We're often trying to find the related acute angle. Not trying to find. Trying to find implies that it's hard to find. We often want to know the related acute angle, the reference angle, and so you just figure out what it is, like really fast, and then know. So that in this case, 235, its related acute angle would be 55 degrees. The difference of 235 and 180. 180 plus 55 would give you the full angle, so 55 is the related acute angle. And then, if you're in the fourth quadrant, how are we going to find beta here? So if we did that minus 270, it would give us this piece. It's not the piece we want. Yeah. The related acute angle is always the acute angle that your terminal arm makes with the x-axis. We're not interested in the angle it makes with the y-axis. It's always the x-axis, and either positive or negative.
So you would need to answer these questions correctly. You need to be given theta or beta, right?
Oh yeah. So in this case, it's 360 minus theta, because if I went 360, but then took away this part, I would be left with only that part. That's my beta. Okay. So that equals beta. That's your little mini formula if you're in the fourth quadrant.
I'm just going to get Sophie. She's downstairs and she doesn't see that water.
So that's those are your 4 little mini formulas. Write them down if you wouldn't be able to derive them yourself. But I encourage you to use visualization and logic to derive them yourself, to build those formulas yourself. Because that's the type of math fact that's easy to forget, but easy to find. Yeah. So you wanna have a way to find it when you forget it. Okay, let's keep going. So here are the angles, and oh, you're gonna take a picture? Go for it. Go. 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 Go.
My
Yeah,
phone's
yeah,
too slow. Ready? Sorry,
Mm.
relax, relax. It's such a shame.
Questions about this idea?
Relax.
Oh, really? Okay. So what we're gonna find is like if I have 150 and I want to know what's the sine of 150, I know it's going to be the same as sine 30. It'll be the same as the reference angle because 150's sine is also going to be positive, just like 30, and they will share all the trigonometric ratios. Cosine 150 is going to be the same as negative cosine 30. And tangent 150 is going to be the same thing as negative tangent 30 because there's a sign flip for those two trigonometric functions. Let's keep going. So here are the angles in standard position that have reference angles of 20 degrees, just to show you. There's one in the first quadrant. The reference angle 20 degrees also has angle 20. And then 160 also has an angle 20 as its reference angle. 200 has 20 as a reference angle, and so does 340. And you can imagine how those formulas would produce all of those, right? This one is, for example, 180 minus 160 gives you the reference angle of 20. This one is 200 minus 180 gives you the reference angle of 20. Let's keep going. All right, so find for me the related acute angle for these obtuse angles here. I have 3 obtuse angles. Tell me their related acute angles. While I play Jeopardy music in my head. 45? How do you know this? You had it too, eh, Fisher? You had that one too? Clearly, yeah. Fisher, 45. Is it because you've been spending so much time with barbells? And you were like, well, I know that if I put weight on the barbell, that could be like 40. That's the bar, 45. That's the 90. So that's like one plate. So that's like a barbell that's really unevenly weighted. And then this would be the second 45-pound plate to give you 135. Related acute angle is this 45-degree angle there. 45.
How would you know
Yes.
which reference angle it's talking about? This one or this one if it doesn't tell you?
It's always with the x-axis. It's never with the
And
y-axis.
picture like you got a windshield and it has to be under the windshield.
For what?
It's the snow
Yeah.
that picks up.
330 degrees. What's its related acute angle?
30.
30. How did you do it, Avery?
330 minus, no, 360 minus 330.
Yeah, that's good. Yeah, 360 minus 330. Cool. So this is 30 degrees.
Wait, so
Great.
why is the reference angle on the x-axis is not like the
Not ever with the y-axis?
Well, no, not the
Oh.
negative x-axis and not on the positive axis.
Oh, because well, if I look at something that had a negative 30 degree or something that had a positive 30 degree, and I compare their trigonometric ratios here, okay? So Caden is jumping ahead a bit with his question, but it's good. We're happy about that. Here's 30 degrees, right? And if this arm here was 1, then this would be 1/2. And then this in here would be the square root of 3. Okay, this would be negative 1/2 going down there. And this would still be 1, and that would still be the square root of 3. This is what we call a special triangle, and the right angle is over here. Okay. Wow, my triangles are ugly, but I zoomed in after I drew the triangles, so that's in my defense. Okay. If I look at the sine of 30 degrees, and I want to compare it to the sine of 330 degrees. Note that this is 330 degrees there, or negative 30. Okay. Well, the sine of 30 degrees is going to be opposite over hypotenuse. Is going to be 1/2 over 1. Or that's just equal to 1/2 or 0.5. You will be very comfortable with. Okay, and then sine of 330, well, that would be this opposite over this hypotenuse. So that will be negative 1/2. So what we have is the sine of 30 degrees is equal to negative the sine of 330 degrees. So we could get there as well by applying the cast rule. See how if I apply the cast rule here and I say, okay, I know that only cosine is positive down there. All of them are positive up there. So everything is going to be the same about this trigonometric value and that trigonometric value, except the sign is going to be opposite. Caden, if I start messing around with this, I'm not working with 330 anymore. I'm working with 60 degrees, and 60 degrees ain't nothing related to 330. Okay, so there I'm just not looking quite in the same spot. We kind of have a standard spot that we're looking at. That's why the reference angle is always with either the positive or negative x-axis.
Right.
240 degrees. What's the 60, eh? Yeah. Okay, so 240 minus 180 is 60. Very good.
Why is it 60?
Because it's 240
Yeah.
minus 180 equals 60.
What would be wrong?
We are using the x-axis.
What would be wrong with 240 minus 1? Or 240 minus? Oh wait.
Minus 270.
So that there is 60 degrees over here.
270 minus 240. Oh, because then you're. Oh.
So it's its distance from the y or x-axis.
Yeah, it's that angle that it makes with either the positive or negative. The acute angle it makes with either one of the x-axes. Yeah.
Because it's on the left side of the y, it's going to be obtuse on the right. Oh, it has to be.
Yeah. Yeah, it's going to be obtuse. And if it's not in the first quadrant, it's obtuse or like reflex. Determine the angle in the specified quadrant with the given related acute angle. If I have a 70-degree acute angle and I'm in quadrant 3, what am I?
You are theta minus 180.
Wait.
We could use our formulas here, but it's just so fast to visualize.
90, 180, 90, 180, and then 180 plus 2 still.
Yeah. You imagine it here.
90.
You say, I'm in the third quadrant, so I'm down there. So I'm 180 plus 70. Like that. 250. Does that make sense, how we get to 250 there?
Yeah.
And I really encourage you to visualize it and build your formula from the visualization every time. That way you don't have to memorize. You just have to remember that a straight line is 180. But anyway, and then 54 degrees, but we're in quadrant 4.
270 plus 54.
No, we're in quadrant 4. Oh, 270 plus 54?
Yeah.
No.
Why not?
360 minus.
Because this is what 270
Oh, yeah.
minus, this is what 270 plus 54 is. It's like up there.
Yeah.
But we want the acute angle there. That's where our reference angle is. Yeah, it's always going off the x-axis.
360 minus 54.
Yeah, so what is it? 306, good. There we go. Oh, hi, Zoe. Livia, do you have a question about that one?
For the last one, 240 degrees, how do you get 60 degrees as the reference angle?
Oh, up here?
Yeah.
240? Oh, because it's 180 plus another 60.
When you do 270 minus 240,
Yeah.
Sorry?
when you do 270 minus 240,
No, because that's worried about the y-axis. We're always looking for the angle it's making with the x-axis to find the related acute angle, to find that reference angle.
149.
And so the x-axis is either 360 degrees or 0 degrees or 180 degrees. $31 degrees, but I'm in quadrant 2.
149. No?
149 is good. So what I imagine Ben has visualized is going there 180 and then saying, but I need to go back 31 degrees. So if you go back 31 degrees, you're going against the flow. That would leave you with 149 degrees. Like this. And if I have a related acute angle of 12 degrees, but I'm in quadrant 1,
Yeah, but 12 degrees.
you're just 12 degrees. That's right. 12 degrees. Because here I am 12 degrees. the angle is the reference angle. Cool. So now I have 8 minutes to give you the bigger bit of this whole lesson. It looks like this lesson should not happen on the same day as the quiz. So we'll know that for next year. Because it's a little longer, this lesson.
For next year?
To me, this is like, yeah, I teach this next semester, so I won't do this to them next semester. So, yeah. So let's take a look. If we're given a coordinate point and we want to know what angle does this coordinate point make as the end of a terminal arm, this is how we do it. Blah, blah, blah. Did I give you these steps on your thing? Yeah, I did. Okay. So let's take a look at an example. Solve the angle in standard position whose terminal arm passes through the point P negative 6, 5. So here's 1, 2, 3, 4, 5, negative 6, and 1, 2, 3, 4, 5. Okay, there it is there. All right, let's find this angle theta. Okay, and when it says solve the angle, that means tell me the angle and tell me all of its trigonometric ratios. So here, what I would do is I can say, all right, this here is positive 5. This here is negative 6. And so I have an angle that's in here, my reference angle beta there has an adjacent that's negative 6, an opposite that's 5. And what's this arm here? Well, that arm is how long the hypotenuse squared would be equal to negative 6 in brackets squared plus 5 squared. So h squared would be 36 plus 25. H squared is equal to 61. And it's a positive, so I know that h is the positive square root of 61. I can throw out the plus minus. I don't need that here because I know h is necessarily positive. It's a distance. So that's going to be a 7 and a fair bit. It's going to be like 7.7 or something. But I can just keep this as an exact value and use it for all my calculations.
Why don't you just do tan?
Yeah, I can just do tan as well. But I'm also going to want to be able to say the following. Sine of theta is equal to opposite over hypotenuse. Cosine of theta is equal to adjacent, which is minus 6 over hypotenuse. Notice that cosine is negative there. Oh yeah, because this point up here had a negative y value. It was 5, negative 6. So it has a negative y value, and cosine seems to be related to these x values. It's not a y. I'm doing it again. I'm doing my x and y inversion thing again. So I have this bad habit. This is minus 6, 5. There we go. That's the point. I graphed it correctly. And its x value here. Its x value is related to its cosine. That's why only sine is positive over here. Tangent would be positive down here. Cosine would be positive over there. And all of them are positive over there because of where x and y is positive and negative. Okay. Here, cosine turns out to be negative 6 over root 61. And tangent of theta is opposite over adjacent. So that would be 5 over negative 6. So both tangent and cosine were less than 0. Sine was greater than 0. And that would be those angles. If I want to find what that angle is, let's do sine inverse of this here. 5 over root 61. So this should give us theta, right? Let's see what it gives us. Okay, clear. Okay, 5 divided by 61, and I take the square root of it, equals 0.64. I can take the sine of that because it's between 1 and negative 1. So take the sine inverse of that. This angle here is 39.8 degrees. It's about 40 degrees. Does this look like 40 degrees, everyone?
No.
40 degrees?
No.
No, what is it then?
It's like 130.
39 subtract 180.
What? 90 plus 40?
It's 140.
140.
Good. When we did this, it told us theta was equal to 40 degrees, but we know that's not quite right. We would quite rightly question that because we know it's bigger than 90 but less than 180. We know it's in the second quadrant. This is solving for the related acute angle. That's why it's important. So now to determine that exact angle, we would use our formula 180 minus 40 and find it to be 140. So therefore, theta equals 140 degrees. And that's it for today. Better pack up, everyone. Thank you very much for your
Wait, Mr. Jennings, could you have
attention.
tan as well?
I could have used any of them, yeah.
But you get a negative